We're going to talk about families of curves today. Remember that there'll be no class for just this class on Wednesday. Okay, so this class is canceled on Wednesday. Next week is test 3 coming up. So we'll have one more lesson on Monday, a review Wednesday, and then test 3 Friday of next week. No, it's going to be everything since test 2. So implicit functions, related rates, linear and quadratic approximation. So everything that was just on that quiz you just got back, right? And then also what we're doing today and what we're going to do Monday. Yeah, and related rates. Yes, you do. It was all on the quiz. Okay, so also don't forget project 3, your data project is due today. Just put it in your folder before you go. Okay, so in this class, we're going to use calculus to understand the behavior of a whole family of functions, and we're going to be able to find a member of a family of functions that has some specified properties. Okay, so a formula such as ax squared plus bx plus c describes a family of functions, right? So this particular example is the quadratic family of functions. A, B, and C, when you don't put numbers in them and you just leave them as like these are constants that could be anything, those are called parameters. And so this particular family of functions is a 3-parameter family, because there are 3 parameters in there, A, B, and C. Okay, I want to find a parabola, so I want to find a specific member of the ax squared plus bx plus c family, the one member of that family that goes through the point 1, 4, and whose tangent lines at x equals -1 and x equals 5 have slopes 6 and -2. Okay. So if I have a 3-parameter family and I want to find a specific member of that family, I'm going to have to solve, I'm trying to figure out what is A, B, and C. So I have 3 unknowns. If you have 3 unknowns, how many equations do you need to be able to figure out what they are? 3 equations. So they have to give me enough information to write 3 equations. And they have given me 3 pieces of information. They told me it goes through the point 1, 4. That's a piece of information. And then I have slopes of tangent lines at 2 different points. At x equals -1, slope of 6. And at x equals 5, slope of -2. So let's just write down what those things mean. Okay, so f of x goes through the point 1, 4. So that means that f of 1 should be 4, right?
You would have had the most difficult way. Yeah, I know.
All right. So if it goes through the point 1, 4, that means f of 1 has to equal 4. So f of 1 means put a 1 in for all your x's in ax squared plus bx plus c. So this is going to be a times 1 squared plus b times 1 plus c has to equal 4. And then simplify this, and it just says a plus b plus c equals 4. So it's one equation, one of the equations that I can generate from the given information. Because I have 3 unknowns, I need 3 equations. So I go to my next piece of information. The tangent line at x equals -1 has a slope of 6. What mathematical object measures the slope of a tangent line? The derivative. Okay, so I need the derivative. F prime of what should be what? F prime of -1 should give me 6. The slope of the tangent line when x is -1 is 6. So f prime of -1 is 6. All right, so I'm going to have to take f prime of x. I'll write it up here. Which, just do the power rule. You bring the 2 down. A is a constant, so it gets copied. 2ax plus b. So f prime of -1 means put a -1 in for the x values. So if I put in a -1 for that x, I get 2a times -1 plus b equals 6. Or -2a plus b equals 6. So there's a second equation. So now I have 2 equations. I need one more because I have 3 unknowns. And my last one is that this tangent line at x equals 5 is -2. So that means that f prime at 5 should be -2. So if I plug a 5 into f prime for x, I get 2a times 5 plus b, it's supposed to be -2. So 10a plus b equals -2. So I have 3 equations and 3 unknowns. How do I solve this? Substitution or elimination? Yeah. Let's see. If I look at, ignore the a plus b plus c for a minute, because that's got 3 unknowns in it. The other 2 equations only have 2 unknowns, a's and b's. So I can solve them either using substitution or elimination, whatever your favorite is. Sure, I can do that. B equals 6 plus 2a. Then you go over to this equation and replace the b with a 6 plus 2a. 10a plus 6 plus 2a equals -2. So 12a equals -8. 8 over 12 reduces to 2/3, -2/3. Okay, so we've got a value for a, that's good. Plug it into the other equation that we just solved for b in terms of a, yep. So b is going to be 6 plus 2 times -2/3. So b is 6 minus 4/3. Well, 6 is 18/3 minus 4/3 would be 14/3. And now I know a and b, so I can put them into my equation that has a, b, and c in it and solve for c. So -2/3 plus 14/3 plus c equals 4. So that's 12/3, which is 4, right? 4 plus c equals 4, so c has to be 0. So I have found a function, I found a quadratic that satisfies all the criteria. F of 1 is 4, f prime of -1 is 6, and f prime of 5 is -2. So see if I can find a spot to just write the answer here. So my final answer is f of x equals -2/3 x squared plus 14/3 x plus nothing because c is 0. So that's my answer. I just was plugging into ax squared plus bx plus c the values of a, b, and c we just found. All right, so I'm going to give you one to try, and then we're going to come back and do some more demo together after you do this one example on your own. Okay, so I want to find a function that looks like a times t plus b over t that has a local minimum at 312. Okay, so you know 312 is on the graph, right? So that means that f of 3 has to be 12. And you know that 312 is also a minimum point. And what is the slope of a tangent line at a minimum point? 0. 0. A minimum point on a graph has a horizontal tangent line, which means that the derivative is 0 there. Okay, so that means that f prime of 3 has to be 0. So those are my 2 pieces of information. That's all I need. I just need 2 because I have 2 parameters to solve for here, a and b. All right, so f of 3 equals 12. That means if I go to my original function f and plug in a 3 for t, I get 3a plus b over 3 equals 12. So that's one equation. And to get my other one, I need the derivative. So I'm going to take the derivative of f. What's the derivative of at? A. If t is our independent variable, the derivative of at is a. And what's the derivative of b over t? Negative b over t squared. Just think of that as b times t to the negative 1. Do the power rule. So you get negative b over t squared. So then f prime of 3 means plug a 3 into the f prime formula for t. So I get a minus b over 9 equals 0. So there's my other equation. Both of my equations have fractions in them, right? It's fine if you want to work with fractions, but most people prefer not to. And it's easy to make mistakes with fractions. So what I'm going to suggest is that we start by multiplying both sides of the equation by 3. That way I get rid of all the fractions. So 3 times 3a is 9a. 3 times b over 3 is b. So I have 9a plus b equals 36. And then my other equation, what should I multiply both sides by? 9, if I want to get rid of my fractions. So I have 9 times a is 9a. b over 9 times 9 is b. 0 times 9 is 0. Okay. So I have 9a plus b is 36, and 9a minus b is 0. The fact that one of my equations has a plus b and one has a minus b means elimination is going to be a really easy method to do here rather than substitution. So I'm just going to copy my 9a plus b underneath my 9a minus b. Add my two equations together. 9a and 9a makes 18a. Negative b and positive b make 0, so the b's go away. 18a equals 36. Divide by 18, and you get a is 2. And now that you know a, you can use any equation that has both a's and b's in it, plug in for a, and solve for b. So I'm going to use this one just because I have some room underneath it. So this is 9 times 2 plus b gives me 36. 18 plus b equals 36. Subtract 18 from both sides, and b has to be 18. Okay, so my final function is f of t is 2t plus 18 over t. Just replacing a and b with the numbers we solved for. Kind of make sense? I feel like pretty much everybody had the two equations and they were just struggling with the solving. Two equations, two unknowns. Just takes a little bit of practice. Yeah. Then you got it wrong. Yeah. I'll look at your work after if you want. Yeah. All right, let's see. Let's start our next part of the demo. So I'm going to look at a little bit more complicated family of functions. Your textbook talks about this family in the reading. E to the negative x minus a squared over b. So this function is related to a useful tool in statistics called the normal density function. It's more colloquially known as the normal curve. So you might have seen it before somewhere. But we're just going to analyze f of x equals negative x squared over b. We're going to ignore the minus a there because that minus a just makes a horizontal shift, left or right a. So I'm going to analyze it without that, and then once I know everything about it, I can just shift it left and right. All right, so I'm going to assume b is positive throughout our analysis. I want to find local extrema as well as concavity and end behavior for this graph. And then once I know all those things, I should be able to draw a pretty accurate picture of this normal density function. Okay, so I want to start with end behavior. So I want the limit as x goes to infinity of e to the negative x squared over b. Okay, so as x gets really, really, really big, what's happening to e to the negative x squared over b? It gets really small, yeah.
It's infinity or negative.
Yeah, so it's this numerator is getting really big, but negatively, right? So it would be, this is bad notation, but it's like this is what's happening, right? It's going e to the negative infinity. So what is that? What happens when you raise e to a big, big, big negative number? It goes to 0, yeah.
Did you write that down, or just not write that?
You can write it down if you want, yeah. All right, then what happens if x goes to negative infinity?
Negative, still negative infinity.
It still goes to 0, yeah. Because the order of operations says you have to do squaring before multiplication, right? So I have to square whatever I plug in for x before I make it negative. So now I'm plugging in negative things for x, but when you square a negative thing, it becomes positive. So basically, plugging in positive numbers and negative numbers for x give you the exact same thing in this function. Because squaring a positive or a negative gives you the same result. So this also goes to 0.
Why is it bad notation?
Because it doesn't really mean anything to write raising something to the infinity, because infinity is not a place you can get to. So I just couldn't leave that up there without making a note that it's not right. Okay, so I know the end behavior. The end behavior approaches 0 at the left and the right ends. All right, let's look at extrema, local extrema. Okay, how do we find local maxes and local mins? What do we look for? Looking for places where the derivative is 0. Yeah, because any place where the derivative is 0, you have a horizontal tangent line. Okay. Also, we look for places where the derivative is undefined because you might have a sharp corner that's a local max or min. So I got to take the derivative and set it equal to 0. So let's see, the derivative d dx of e to the negative x squared over b. Okay. So what's the derivative of e to some stuff? E to some stuff times the derivative of the stuff. So my derivative is going to be e to the negative x squared over b, e to the stuff, but then I still have to multiply by the derivative of the stuff. Right? I didn't even try to take that derivative. I just wrote down times the derivative of the stuff. I'll take the derivative in the next line. Okay, what's the derivative of negative x squared over b? Close. Just negative 2x over b. Yeah. If it helps, right, think of negative x squared over b as negative 1 over b times x squared. And then you can just do the power rule. Negative 2 over b times x or negative x over b. So this is e to the negative x squared over b times negative 2x over b equals 0. All right, so this is handy because it's already written in factored form. Right, so I'm multiplying two quantities together here, and the answer is 0. The only way that can happen is if one and or the other quantity is 0. Right, so either e to the negative x squared over b is 0, or negative 2x over b is 0. How about this first equation? What x value will make that 0? None, right? An exponential function will never be 0, right? We know what exponential functions look like, or like this, if it's growth or decay. They never hit 0. 0 is a horizontal asymptote. It never gets down to 0. So this never has no solutions. Negative 2x over b, that happens only equals 0, only happens if x equals 0. So that's my location of my max or my min, right? Do I know it's a max or a min?
Because there's no way the first equation is negative.
Supposed to be a max without both x zero is 0.
Well, it could be negative. Yeah, it could still be a min.
Like if you plug anything to the first equation, it's always going to be positive.
Ah, okay. So if I combine your two statements, I can prove it's a max. If you look at the original equation, e to some stuff, always going to be positive. Can't get a negative, right? Because it's always going to be above the x-axis, if it's growth or decay. It always lives above the x-axis. So no matter what I plug in here, it's got to be positive, which means that when I plug in 0, it's got to be positive, right? And I know the end behavior approaches 0. Okay, so it's got to look something like I've got a positive value at 0, and my end behavior looks like this. So it has to be a max.
Because it's an e to the x function, it's never going to be negative.
Right. E to anything will never be negative. E to a negative, e to 0, e to a positive, e to a fraction, always going to be positive. Another way we could tell that that was a max would be to take the second derivative. And then if the second derivative at 0 is positive, that means that the function's concave up, which means it would be a min. If the second derivative at 0, the x value in question, is negative, that means function's concave down, and you'd have a max. And part of this question is going to ask me to analyze concavity, right? I was supposed to find local extrema and concavity, right? And the second derivative deals with concavity, so I have to take the second derivative anyway. So maybe I'll just verify that this is a max by taking the second derivative. All right, so let's see. F of x was e to the negative x squared over b. I've got that. F prime of x was e to the negative x squared over b times negative 2x over b. So I'm going to take the second derivative now. So how am I going to take the second derivative of this? The product rule. Yep. So I've got first e to the negative x squared over b times the derivative of the second, which would be negative 2 over b, plus the second, negative 2x over b, times the derivative of the first, the derivative of e to the negative x squared over b, e to the negative x squared over b, times negative 2x over b, the derivative of the stuff. So that's my second derivative. That's what's going to tell me about concavity. So what I'm interested in right now is the concavity when x is 0, because that will tell me whether I have a max or a min. If it's concave down, it's a max. If it's concave up, it's a min. We did. I'm just doing it another way, just to verify. All right, so if I put in a 0 for all my x's, e to the 0 is 1 times negative 2 over b. plus negative 2 times 0 over b is 0. So then it doesn't even matter what those other two values are because I'm multiplying them by 0. And I get negative 2 over b. Remember, we're assuming b is a positive number. So negative 2 over b, positive or negative? Negative. So that means the function is concave down at the extreme value, which means that x has to be a max. Okay. So just another way to verify that that's a max. And the reason I decided to do that was because I needed to take the second derivative anyway to find out if I have where my concavity is, where the function is concave up and where it's concave down. Okay, so concavity. I can find changes in concavity when the second derivative equals 0. So that's what I'm going to look for. I want to set f double prime equal to 0. So f double prime is this whole thing. Okay. So I've got an e to the something in both terms. I'm going to factor that out. Factor out e to the negative x squared over b. And what I'm left with in the first term is just a negative 2 over b. And in the second term, a negative 2x over b. And I liked doing that because that means I now have it written as a product. Two quantities multiplied together, the answer is 0. That only happens when one or the other is 0. This one we already established is never 0. And then this one I can solve for x. Yes. I did. Did I? Hold on. Yes, I missed another negative 2x over b. Thank you. Yeah, okay. So when I factor out that, I'm left actually with a negative 2x over b times another negative 2x over b, which is positive 4x squared over b. There we go. Yeah, so I'm going to multiply both sides of this equation by b. Hate fractions. So I have negative 2 plus 4x squared equals 0. All my b's just canceled. So 4x squared equals 2. X squared equals 1/2.
I totally lost Jeff.
When I fixed it.
Well, no, I was just trying to like catch up and then you went back. I got the double.
Equals 0.
Yeah.
Right, okay. So then I pulled out the e to the negative x squared. I said there's one of those in both terms. So I just factored it out, right? Yeah, I'm just factoring it out like reverse distributing. And then what's left after I remove that, in this term, I'm just left with a negative 2 over b. So that's why I wrote that there. And then in this term, after you remove the e to the negative x squared over b, you're left with negative 2x over b times negative 2x over b. And when you multiply them together, you get positive 4x squared over b squared. Shoot. Okay. Ah. All right, so I'm going to multiply both sides by b squared to get all my b's to cancel. So I have negative 2b plus 4x squared equals 0. Yeah, I could, or 4x squared equals 2b, divide by 2, so x squared equals, divide by 4, I mean, so b over 2. So x is plus or minus the square root of b over 2. Ugh. All right, what are those x values? What was I just solving for? I set the second derivative equal to 0 and I solved. What happens when the second derivative is 0? I was looking for changes in concavity. Yeah. So these are inflection points. Changes in concavity. Okay. Plus or minus root b over 2. So let's see if we can take all the information we have and sketch this function. F of x is e to the negative x squared over b. All right, so I know it's got a maximum up here at 0. And I know it approaches 0 as its end behavior. But it's always positive, so it's never going to go down below the x-axis. Okay. And then it's concave down here because that's a max. And it's going to, it has to at some point change concavity in order to come down and approach 0. So it's concave down, and then at some point it switches to concave up. And that place where it changes from concave down to concave up is the square root of b over 2. And then it's going to do the same thing on the other side. And that is the normal curve, normal density function. So there's nothing else on this slide. You want me to go to the previous slide? Yeah. All right, so that was a really tricky analysis. Now I'm going to let you do a kind of less tricky, but harder than the first example on your own.